Hi and welcome to exercise 8.5 where we're going to finally get around to doing differentiation using shortcut techniques rather than by first principles. And this is what you're going to do the majority of the time. Most times you are not going to be worried about using differentiation by first principles. That takes way too long and it's way too difficult. So we've already covered that there are many different ways we can describe the gradient. Well, the derivative is actually a very similar description to gradient, so let's have a look at the words that we've already covered. We've got slope, gradient, steepness, m, rise over run, y2 take y1 over x2 take x1, and tan theta. They're all the ones that we've seen before. Now here are some new terms that are effectively the same as gradient. The derivative. Well, finding the derivative is actually allowing you to find the gradient ultimately. The gradient at any point on the curve. F prime x or f dash x, y dash, dy dx, they're all abbreviations for the derivative. So let's talk about the basic rule. When you actually deal with differentiation, the first thing that we need to make sure we understand is that we've got ourselves some expression. Now here we've got y equals kx to the power of n. And what we're focusing on is this power of n. We're going to actually move it out the front. So it becomes n times kx to the power of n minus 1. Because what actually happens is that the n, the power, is always decreased by 1. It's multiplied out the front and then it's decreased by 1. So we can see that the derivative of y with respect to the letter x is equal to n multiplied by the original question with the power decreased by 1. And that's the basic premise for differentiation at its simple level. So let's try some questions, and you'll notice that if we need to refer back to the rule that we've got it written up in the top right hand corner, that the derivative is equal to the power multiplied by the original question, but wherever we have a power of x we decrease it by 1. So let's have a look at what we have here. We've got y equals x to the power of 5. Well, the power is 5, so we times it out the front. 5 multiplied by x to the power of 5, but remember the power is decreased by 1, so it becomes 5 multiplied by x to the power of 4. And there's our first differentiation question done nice and quickly. If we had have tried to do that by first principles, that would have taken quite some work because we would have had to the power of 5 bracket to expand out. Would have been a messy question. Let's have a look at our second example, part B. Y equals 3x to the power of 4. So we look at the power, and we times it out the front. So we times the 4 out the front, so you get 4 times 3x to the power of 3. Remember that the power will ultimately decrease by 1. So you end up with 4 times the 3 out the front gives 12x to the power of 3. And there's our answer. Let's try part C. Now this one's a little bit more complicated because we're actually starting with many parts. So we just do each part separately. There is one thing that I'm going to actually point out though before we start, and that's the 5x term in the question. That's effectively 5x to the power of 1, and the 2 doesn't have an x, so it's really like an x to the power of 0. Let's see what happens when we look at each term individually. Let's look first at our 2x to the power of 6 term. The power 6 multiplies out the front. 6 multiplied by the 2 out the front gives 12x. The new power is 5 because you always decrease it by 1. So you get 12x to the power of 5. The second term that we're going to look at, the x to the power of 4. The 4 gets multiplied out the front, so it becomes 4x to the power of 3 because the power is decreased by 1. Our next term, minus 3x squared. Well, we look at the power. The power is the 2. We multiply it out the front. 2 times negative 3 is negative 6, so it becomes negative 6x to the power of 1 because the power is decreased by 1. Now the 5x, you notice I put a 1 above it because the power above the x is a 1. We just don't normally write it. 1 multiplied to the 5 out the front becomes 1 times 5 is 5x to the power of 0. And the last term, the 2, well, because the x is to the power of 0, when you multiply the 0 out the front, you get 0 multiplied by something, and 0 times anything is always 0, which means that we don't even have to worry about differentiating that part because the answer is going to equal 0. Whenever you differentiate a constant, that means when you differentiate a number, the answer will always be 0. Let's just tidy this up a little bit because really don't want to write the question as 6x to the power of 1. I'm going to write that just as 6x. And 5x to the power of 0. Well, we know x to the power of 0 is 1. So 5 times 1 is just 5. So we tidy that up. Let's go on to part D. Now this is the first of the questions that we can't actually differentiate quickly using our method while there's a bracket there. So we've got 2x plus 1 in brackets squared. And that creates a problem, that's squared. So what we're going to do is we're actually going to expand the brackets out. Now you might remember the shortcut for expanding the brackets. Square the first term, 2x times 2x gives 4x squared. Multiply the two terms together and then double that result, 2x times 1, 2x, double it, you get 4x. And the last term, square it and you get 1. So we end up with 4x squared plus 4x plus 1. And now we can differentiate. So let's differentiate the first term. 4x squared. The 2, which is part of the power, multiplies out the front. 2 times 4 gives 8x to the power of 1, which is better written as 8x, which I'll write in a moment. The 4x term, well, the power above the x, there's a 1 above it. We don't have to actually write it. We don't normally write it, but there's a 1 there. 1 times 4 becomes 4x to the power of 0. The 1 on the end, we said that if it's a constant on the end, there's no x part, so we get 0 as our derivative. Let's just tidy that up. Becomes 8x plus 4, because x to the power of 0 we know is 1, and 4 times 1 is 4. So example D was fairly simple once we took into account that we had to expand the brackets out. We can't differentiate when the brackets are there with a power of 2 above it. So if you get a pair of brackets, we have to expand it at this stage. Later on we're going to learn another technique which might be able to help avoid doing that. But for the moment, you're going to have to expand the brackets. Let's go to example number 2. Example 2 says f of x, which is another way of writing y. So f of x equals x cubed plus 2x squared, take 4x plus 1. We have to find the derivative when x is 2, f dash 2. The derivative when x is 2. Now we never find the derivative when x is 2 straight up, or we don't find that part straight up. We find the derivative when it's x. We find f dash x. So in other words, we differentiate. Let's have a look. The first term is an x cubed. Differentiate x cubed, the power is a 3. Multiplied out the front, you get 3x squared, because the power has to go down by 1. Let's look at the next term, the 2x squared part. The power is a 2. Multiply the 2 to the 2 out the front. 2 times 2 is 4. You get 4x to the power of 1, which is just easily written as 4x. The next term in our question, minus 4x. So we actually now look at that. Above the x is a 1. 1 times minus 4 gives minus 4x to the power of 0, which is better written as just minus 4. We don't worry about the x part because x to the power of 0 is 1. The plus 1 on the end, the constant term, well, constants become 0 when we differentiate them. So that is the derivative with respect to x. That's f dash x. That's the derivative with x. Now let's focus on what the question wanted us to find. It wanted us to find the derivative when x is equal to 2. So that means everywhere we see an x now, we look at the x and we think, well, we've got to replace that with the number 2. So we replace every x with a number 2, which means that the derivative when x is 2 is equal to 3 multiplied by 2 squared plus 4 multiplied by 2, take away 4, which when you put into your calculator or your process gives you an answer of 16. So the derivative when x equals 2 is 16. And there's our answer. If we actually have a look, this is actually what graphically we've just done. You'll notice that we've got the curve here, which is, or the graph here, which is the cubic. Y equals x cubed plus 2x squared minus 4x plus 1. We wanted to find the derivative when x was equal to 2. Now when x is equal to 2, we go up from the x value of 2, and there's our point where x equals 2, just there. We can actually draw our tangent in, and that tangent, that green line, has a gradient of 16. The gradient at the point where x equals 2 is equal to 16 when we're talking about our original curve. You don't have to draw the curve every single time, that's just a representation of what we've actually done. Example number 3. Let's have a look at example 3. Now with example 3, we've got a problem. And the problem is we cannot differentiate if we have x in the denominator. Not like this. Not using our technique. So what we have to do is look at that question and recognize that we have 2 parts in the numerator and 1 part in the denominator, which means we could split the question up and treat it as 5x cubed over 3x minus 4x over 3x. It's a common denominator type thing. Let's tidy the question up a little bit. If we actually look at that, you're going to actually spot that and say that x can cancel with one of the x's there, and that x will cancel with that x. So we end up with 5x squared over 3 minus 4 over 3. Now 5x squared over 3 can sometimes confuse people. I normally leave it like that, but you can also think of it as this: 5/3 of x squared minus 4 over 3. Well, now we're ready to differentiate. Now with this question, instead of writing f dash x, you'll notice I've written y dash. The reason I wrote y dash was because the original question wasn't written as f of x, it was written as y. You could also have written this: dy over dx, the derivative of y with respect to x. But it's probably easier to write it as y dash because it's just a lot easier to write. Okay, so what actually happens there is we look at our question now, and whoops, let's just get rid of that. I went too far, but that doesn't matter. Let's look at our original question. This is the question now because we've modified it. We have to differentiate this. Well, let's look at the power above the x. It's 2. So 2 gets multiplied to 5 over 3. 2 times 5 is 10, so you'll get 10 over 3 x to the power of 1. So you get 10 over 3 x. Remember, 4 over 3 is a constant. There's no x part in it, so when you differentiate a number, you get 0. So there's our answer. Example number 4. This is a little bit trickier because we're now differentiating with respect to the letter R. A different letter, but that's okay. That means in the question we should have the letter R. So that's a little bit like having an X in the previous questions. So let's actually set it up now. Now we're differentiating S with respect to the letter r. So that's ds over dr. The derivative of s with respect to the letter r. Let's actually have a look at the question now. Remember, we're looking with respect to the letter r. So let's look at the powers above the r's. Power above that r is a 2. So the 2 gets multiplied out the front. 2 times 2 is 4, so we'll get 4 pi r to the power of 1 because we decrease the power. So we get 4 times r, 4 times pi r. The next part, well, we're focusing on the r. Now that r has a 1 above it, so the 1 gets multiplied to the 2. We get 2 pi h, don't worry about the order, and the power above the r becomes a 0. So you just end up with 2 pi h, and there's our derivative with respect to r. So we've played around with differentiation using a shortcut technique. It's now time to do your questions. Have fun.